Hi everyone, and welcome back to the MCAT A series of lectures in physics. In the previous two videos, we looked at individual charges and the fields created by them, that is, electric and magnetic fields. In this video, I would instead like to focus on the movement of a collection of charged particles, in other words, a current and its flow through what are known as electronic circuits. I likewise also introduced the idea of voltage in terms of individual charges, and I would now like to describe it in terms of current. The idea of resistance will then be introduced, which describes how difficult it is for this current to flow through a circuit. Capacitance, in other words the ability for a circuit to store electric charge, will then be discussed in detail. Conductivity, in other words the degree to which a particular material conducts electricity, will then be considered. Finally, I shall look at different meters, which are used to determine the current, the voltage, and the resistance of different components within a circuit. I have already given a rough definition of current in the previous two videos. I described current as the flow of charge, that is, the amount of coulombs that pass a particular point every second. In other words, if I have a wire as I've drawn here, and charged particles flowing to the right, then the current is defined as the total charge passing a particular point per unit time. In other words, charge Q divided by time t. Current therefore has units of charge per time or coulombs per second, but again, instead of writing coulombs per second all the time, we define an ampere as a coulomb per second. Ampere is the unit of current, and we use the symbol capital A to represent it. I also stressed in the previous videos that it is electrons that typically flow when we are talking about electricity. Therefore, in this diagram I've drawn here, these charged particles are typically electrons. However, due to convention, we instead define current as the flow of positive charges, even though it is the case that it is actually the negative charges which flow. To understand what this means, allow me to draw a very simple circuit. Let's assume that this circuit is simply composed of a battery and a wire. A battery is represented here by a long vertical line and a short vertical line, and the wire is the rest of the circuit, this black rectangle as I have drawn. Physically, what actually happens is that the electrons flow from the small vertical line around the circuit back to the large vertical line. This is the direction of electron flow. However, we say that the electric current instead flows from the large vertical line to the small vertical line as I've drawn here. The large vertical line we call the positive terminal, and the small vertical line we call the negative terminal. Therefore, the current is said to flow from the positive terminal to the negative terminal. However, what is actually happening is electrons are flowing from the negative terminal to the positive terminal. Recalling our definition of electric potential, since electrons are negatively charged, they must be moving from a point of lower electric potential to a point of higher electric potential, thereby overall reducing their electric potential energy. This is because the electrons want to naturally move from the negative terminal to the positive terminal. They have the potential to move around the circuit. After they have done this, they have therefore lost potential energy. However, remember, by convention, current flows in the opposite direction. Therefore, we say that current flows from a higher potential to a lower potential. Therefore, as the electric potential is changing throughout the circuit, that electric potential, in other words that voltage, must be present due to the battery. The battery is the only thing in the circuit. I have already shown you how to draw a battery in a circuit. A battery is simply two vertical lines, one longer than the other. The longer vertical line is known as the positive terminal, and the smaller vertical line is known as the negative terminal. As I said, in a circuit, electrons actually flow from the negative to the positive terminal. By convention, current is in the opposite direction, and therefore current flows from the positive to the negative terminal, from the longer vertical line to the smaller vertical line. Simply having two lines, one long and one short, is the simplest type of battery. It is known as a cell. In general, however, there can be more than one cell within a battery. To represent this in a circuit diagram, we draw one cell, in other words a long vertical line and a short vertical line, dashes in the middle to represent possible other cells, finished with another cell, another long vertical line and another short vertical line. As I stated, such batteries or cells create potential differences, in other words voltages, which gives the electrons the potential to move around the circuit. Even in the case when no charge is moving between the terminals, there is still a voltage in the battery. This voltage is known as the electromotive force, or the EMF, and it is a measure of the energy provided by a cell or battery per coulomb of charge. As voltage is defined as energy per charge, it therefore is a measure of the energy imparted by the battery that causes a current to flow through the circuit. Although it is known as an electromotive force, this is a bit of a misnomer. It is not actually a force, it is a measure of voltage. What actually creates this voltage and energy within a battery is to do with the electrochemistry going on within the battery. This is outside the scope of the physics portion of the MCAT, but is a chapter of the chemistry part of the MCAT, and therefore you should either be comfortable with it now, or you will find out more details about it later. As electrons are moving around a circuit, two things must remain conserved that we have already talked about. There must be both a conservation of charge and energy. If we look at one point in a circuit, the amount of charge to the left of that point must equal the amount of charge to the right of it. The energy associated with those moving charges to the left of that point must also equal the energy associated with the charges to the right of that point. In terms of electric properties like current and voltage, there are two laws that we must know for the MCAT. These laws are known as Kirchhoff's laws. To understand these laws, allow me to draw a very simple circuit. Again, here I have a battery, and this is a very simple battery, it's just one cell, and therefore I have drawn just one long vertical line and one short vertical line. I again have a wire going from the positive to the negative terminal, and this time I have also added in another component. This component is known as a resistor, and I will discuss what it is in more detail shortly. Not only this, however, but I've added in an extra wire that creates a different path that the electrons can flow around. If you have ever seen an electric circuit in real life, then you know how these two wires are connected. They are typically connected by what are known as crocodile clips. If you can't visually picture how these two wires could be connected, I recommend having a quick Google at what crocodile clips are and have a look online at more complicated circuits. I have also added in a second resistor just to make the circuit a bit more complicated, but it is not important to describe these Kirchhoff laws. Remember, as I stated, current flows from the positive terminal to the negative terminal, in other words from the long vertical line to the small vertical line. Therefore, in this circuit, the current is flowing in a clockwise manner, as I've represented here with these red arrows. Again, however, the electrons have in a sense a choice of which of the two vertical lines to go down on the right hand side. Some of them will go down the vertical line that's furthest to the right, whereas others will go down the vertical line just to the left of that. In other words, in both vertical lines, there will be a current of some description. What actually happens at the point of intersection of these two wires, in other words known as nodes, is fully described by what is known as Kirchhoff's laws. The first Kirchhoff law we will look at is known as the junction rule, sometimes also known as the voltage law. The voltage law, if you like, is simply conservation of energy. As I already stated, the battery itself has a voltage, in other words an energy per charge associated with it, known as the EMF. That EMF causes the electrons to move around the circuit, thereby giving the electrons some form of energy. This means that the battery must have lost energy and the electrons moving around the circuit have gained energy. Overall, however, the energy and therefore the voltage must be conserved. Therefore, the exact amount of energy lost by the battery must have been given to the electrons in order to make them move, in order to create a current. This idea is summed up by saying that the sum of voltages around a loop in a circuit is equal to zero. And by a loop, I mean that any path that the electrons can go from the positive terminal to the negative terminal. Therefore, if we assume that the battery has an EMF of 10 volts, then the electrons in a circuit have a voltage of minus 10 volts, minus 10 volts representing the fact that they've taken away energy from this battery. Overall, however, the sum of the voltages is 10 volts minus 10 volts, which is 0. In other words, overall, stating that the sum of the voltages is equal to 0 is simply stating that the total amount of energy gained per unit charge must be equal to the total amount of energy lost per unit charge. The energy gained by the electrons is equal to the energy lost by the battery. What this means for this particular circuit is as follows. Looking at the circuit, we see that there are two different loops that the electrons can use. The electrons can either flow from the positive terminal, in other words the long vertical line of the battery, around the loop to the closer part of the wire on the right hand side, in other words the closer vertical line where there's no resistor, down through the wire and then back to the negative terminal, the small vertical line in the battery. Or it can equally take the longer route, which is go from the positive terminal all the way around the loop to the far right hand side before going back into the negative terminal. What does this mean in terms of the Kirchhoff law? Well, remember we have two different loops here, and we know that the sum of the voltages around each loop must be zero. Therefore, since the only differences between these two loops are the two branches, the two parts of the wire on the right hand side, the voltages through both sections of those wires on the right must be the same. Therefore, the potential difference or the voltage on either branch on the right is equal to the other. This is what we get from using Kirchhoff's voltage law in this circuit. This came about, remember, by considering conservation of energy. However, I also mentioned that there is conservation of charge. What does this tell us in this circuit? Well, to understand this, let us look at one particular node in the circuit, node A, as I have drawn here. Recall, in this circuit, the current is going around the circuit clockwise. Therefore, at node A, there is charge and therefore current entering that node from the right. The current is going right through that node. After going through that node, some of the charge will go through one branch and some will go through the other branch, as shown again by the two arrows leaving node A. How much charge goes through one branch compared to the other branch is determined by the components in each branch. This is described in more detail in the sample passages we have provided for you. However, what is true about this node, and true about nodes in general, is that the charge into that node must equal the charge out of that node. This is conservation of charge. Since current is charge per unit time, this must also mean that the current into that node is equal to the current out of that node. In other words, I sub in is equal to I sub out. For example, if the current into the node was 10 amps, then the current out of the node is 10 amps. The sum of those two currents out of the node must be equal to 10 amps. It could be 5 amps plus 5 amps or 7 amps plus 3 amps or something like that. What determines that, as I said, is the components inside each branch. However, in general, the current in is equal to the current out. This is known as Kirchhoff's current law. Next, I would like to look at another property of a circuit and its components, known as resistance. Resistance, as its name suggests, has to do with how difficult it is for a current to flow through a circuit or a component. It is a measure of that opposition. A very rough analogy is to think of it like a kind of electrical friction or an electrical air resistance. As is the case with temperature, an electrical conductor is something that has a very low resistance. It allows current to flow through it easily, just like a thermal conductor allows heat to flow through it easily. Similarly, in the opposite sense, an electrical insulator is something that has a very high resistance. It does not allow current to flow through it easily. Anything in between these two extremes is known as a resistor. It resists the flow of charge by some amount. I have already shown you in a previous circuit how we represent a resistor on a diagram. We simply draw a rectangle that is joined to either side of the circuit. In general, all appliances can be considered resistors. For example, light bulbs are a very common type of resistor that comes up on the MCAT. A light bulb resists the motion of the charge and instead converts that charge into light. It takes the electrical energy from the circuit and turns it into light energy. The resistance of a simple component can be quantified as follows. Let us assume that the component is of length L and of cross-sectional area capital A. In other words, we assume that this component is roughly a cylinder. As has been the case for many different physical quantities we have discussed previously, resistance depends upon three different factors. It depends on both the length and the cross-sectional area of the resistor, as well as what material the resistor is composed of. As I have already described, some resistors can be considered insulators while some can be considered conductors. Some are very good at allowing the flow of charge, whereas the flow of charge is quite difficult through other resistors. What makes one resistor a good conductor compared to a good insulator is the material it is made from. Therefore, the particular material must in some way be included in the formula for actually calculating the resistance of that resistor. The variable that quantifies a particular resistance for a given resistor is known as the resistivity. The resistivity rho determines how good a resistor is at resisting the flow of charge. Overall, the resistance of a particular component capital R is given as follows. It is equal to that resistivity rho multiplied by the length of the resistor capital L divided by its cross-sectional area capital A. As we shall see shortly, the unit for resistance is volt per amp, but again, instead of writing volt per amp all the time, we define a volt per amp as an ohm. The unit of resistance is an ohm. We use the capital Greek letter omega, as I've drawn here, as the symbol for an ohm, as the symbol for the unit of resistance. Based on this unit, if you rearrange this equation for the resistivity, you will find that the resistivity has units of ohm meter, ohm multiplied by meter. I encourage you to check this in your own time. One final thing to note about resistance is, although it is not clear from this equation, most conductors have a greater resistance at a higher temperature. As the temperature of a solid increases, those particles within the material vibrate more frequently, vibrate at a higher rate. Such vibrations create a greater resistance to current, a greater resistance to the flow of charge. You may wonder, therefore, is the equation we have just written down only an approximation? Is it only true, for example, at certain temperatures? In fact, it is actually true in general. The way the temperature is taken into account with this equation is that the resistivity rho is dependent upon the temperature. Rho is a function of capital T, the temperature. The relationship between the resistivity and the temperature is outside the scope of the MCAT, but you do need to know that such a relationship exists. The resistivity of a material is dependent upon its temperature. Now remember, I have introduced three different properties of a circuit. Voltage or potential difference capital V, which has to do with the potential the charges have to move around a circuit. The current of the circuit capital I, which is the flow of charge per unit time. And the resistance of the circuit capital R, how difficult it is for the charges to move around the circuit. These three quantities are in fact related by what is known as Ohm's law. Ohm's law states that the potential difference or the voltage capital V divided by the current I is equal to the resistance R. This equation can be understood as follows. Let us consider a typical resistor that has a resistance capital R. The voltage across that resistor will be proportional to the resistance of that resistor. Any electrical resistance results in an energy loss across the resistor, in other words, a voltage drop. That electrical resistance, according to this equation, is directly proportional to that voltage drop. Also, it is important to note that this equation can be applied in many different circumstances. It can be applied by looking at just one component in a circuit, by looking at multiple components in a circuit, or by looking at the circuit as a whole. Remember, each resistor has its own resistance associated with it, but as we shall see shortly, it is possible to calculate the total resistance in a circuit, thereby allowing us to use Ohm's law to calculate, for example, the current in a circuit. As current flows through many different resistors, there is a voltage drop associated with each resistor. Finally, one important point to note is that it is not only the resistors in a circuit that have resistance. The wires themselves, although very good conductors, also have an associated resistance with them. That resistance is very small, but it still exists. Even the battery itself will have an internal resistance associated with it. Because of this, the actual voltage supplied to a circuit is less than the voltage of the battery. In other words, the voltage supplied is equal to the EMF of the battery minus the voltage associated with the internal resistance of that component. This will be quantified better in a question at the end of this video. Now, I would like to consider resistors in different types of circuits. Resistors can be connected in circuits in two different ways, either in series or in parallel. Resistors connected in series means that the resistors are directly connected to one another. There is only one loop in the circuit. For each resistor, a wire goes into the resistor and a wire comes out of the resistor. That wire then goes into the next resistor, and so on. We say that all resistors are directly connected to each other, there is only one loop, and the resistors are therefore in series. For such resistors in series as I have drawn here, all of the charges must pass through each resistor. In other words, the current has no choice but to travel through each resistor. As these electrons pass through each resistor, energy is taken from those electrons by the resistor. Therefore, there is energy dissipated and therefore a voltage drop. As there is a voltage drop at each resistor, the total voltage drop for the circuit is simply equal to the sum of each individual voltage drop. In other words, the total voltage drop of the circuit is equal to the voltage drop due to resistor 1 plus the voltage drop due to resistor 2 and so on. Capital V is simply equal to V sub 1 plus V sub 2 and so on. Remembering that Ohm's law tells us that V is equal to I, or the voltage drop across a component is equal to the current going through that component multiplied by the resistance of that component, then we also see that in order to get the total resistance of the circuit, also known as the equivalent resistance, we again simply add up the individual resistances. In other words, capital or the total resistance or the equivalent resistance is equal to the resistance of resistor 1 or sub 1 plus the resistance of resistor 2 or sub 2 and so on. One point to note about this, and hopefully it's very clear from this equation, is that as you add more resistors in series, the total equivalent resistance increases. This may seem like a trivial statement to make, but it is not true for the other way that resistors can be placed in a circuit, as we shall see shortly. Finally, as I have already stated, both the voltages and the resistors add up to get the total voltage and resistance. What happens to the current? Well, as I said, that current passes through each resistor. There is only one loop in this circuit, and therefore the same current must pass through each resistor. Therefore, in terms of the current is simply the same everywhere in this loop, and that current can be calculated using Ohm's law. However, as I have shown you previously, things can get a bit more tricky. There can be multiple loops in one circuit. Multiple loops in the same circuit is created by connecting different components, for example resistors, in parallel, as I have drawn here. Again, if you can't picture how these wires can be connected in parallel, I recommend having a quick Google of typical parallel circuits to see them in action. As I just said, when components are connected in parallel such as this, there is now multiple paths that the electrons and therefore the current can travel through. In a sense, electrons have a choice regarding which path they will take. Some of them will go down one path, while others will go down another path. However, what is true, as I already explained with Kirchhoff's voltage law, is that the voltage drop through each different branch in the circuit must be the same. In other words, the voltage drop across resistor 1 is equal to the voltage drop across resistor 2 and so on. However, while this is true for the voltage drop, it is not true for the resistance. In general, electrons prefer to go down a path of smaller resistance. Hopefully this makes intuitive sense. If it's harder for electrons to travel through a certain path, then more of them will instead travel down the easier path. As there are more electrons traveling down the path of lesser resistance, then the current down that path will also be greater than down the other path of higher resistance. Because of this, there is in fact an inverse relationship between the equivalent resistance and each individual resistance. In other words, 1 over the total equivalent resistance is equal to 1 over the resistance of resistor 1 plus 1 over the resistance of resistor 2 and so on. In this case, and I encourage you to put in sample numbers to check this, the total equivalent resistance will always decrease as more resistors are added in parallel. For a general circuit, of course, we can have components like resistors both in parallel and in series. A question with a complicated circuit such as this will be shown at the end of this video. There are also other examples of complicated circuits in the sample passages we have provided for you. So far, we have covered 2 of the 3 main components that are typically tested on the MCAT, that of batteries and resistors. The third most common type of component that comes up on the MCAT is known as capacitors. Capacitors are components that have the ability to store charge at a particular voltage. One example of a capacitor that I'm sure you're aware of is a defibrillator. In order to operate a defibrillator, it must first charge up. Electrons must first build up on the capacitor. Once it is fully charged, that charge can then be released when the defibrillator is actually used. The MCAT, however, typically focuses on a particular simple type of capacitor known as a parallel plate capacitor. In a circuit, we represent a parallel plate capacitor with this symbol that I've drawn here. Two vertical lines of the same length representing each plate, and individual wires entering each plate. With resistors, we quantify how good they are resisting the flow of charge by using resistance. In terms of capacitors, we quantify how good they are at storing charge using capacitance. Capacitance is measured in farads with a symbol of capital F. A parallel plate capacitor operates as follows. Two metal plates of cross-sectional area capital A, as I have drawn here, are connected into a circuit. When that circuit is switched on, positive charge builds up on the plate connected to the positive terminal, and negative charge builds up on the plate connected to the negative terminal. In other words, there is a high potential on one plate and a low potential on the other plate. This is therefore considered a capacitor as there is charge stored on each plate. The actual value of the capacitance of this parallel plate capacitor is given as follows. It is equal to a constant epsilon 0, which we've seen before when looking at Coulomb's law. It is the permittivity of free space, multiplied by the cross-sectional area of each plate capital A, multiplied by the plate separation, in other words the distance between the plates, d. There is also a separate equation to calculate the capacitance, which is true in general for a capacitor and not just for a parallel plate capacitor. The capacitance of a capacitor in general is defined as the ratio of the magnitude of the charge stored on the capacitor divided by the potential difference across the capacitor. In other words, capital C, the capacitance, is equal to the charge on either plate capital Q divided by the potential difference capital V. For parallel plate capacitors in particular, there is a voltage V applied across the plates, and each plate has collected a charge capital Q. One plate has a charge plus Q, and the other plate has a charge minus Q. One plate is positively charged and one is negatively charged. We can also see from this equation where the unit farad comes from. Capacitance is charge per voltage, and therefore farad is coulomb per volt. As we are storing charge in a capacitor, we are also in a sense storing energy. The main purpose of a capacitor is to store a certain amount of energy in the form of charge separation. The energy stored in a capacitor is true in general, not just for parallel plate capacitors. The energy of a capacitor at a potential difference V is given as follows. Energy capital E is equal to a half multiplied by the capacitance capital C multiplied by the potential difference capital V squared. As there are three equations related to capacitance that you need to know for the MCAT, it is not uncommon in questions on the MCAT for you to either figure out which of the three equations you need to use, or possibly use a combination of the equations to find the correct answer. Therefore, I strongly encourage you to look at the questions we have on capacitance in the sample passages we have provided for you. Just as with resistors, we can consider putting capacitors both in series and parallel in a circuit. Remember, we derived our equations for resistors in parallel and series by considering the voltages. We then used Ohm's law to relate those voltages to the resistances. However, we also know by our definition of capacitance that capacitance is equal to charge per voltage. C is equal to Q over V. Therefore, the capacitance is inversely proportional to the voltage, rather than resistance, which is directly proportional to voltage. Therefore, using just that simple logic, for a capacitor in series, we expect an equation similar to that of a resistor in parallel, and we get just that. For capacitors in series, as I have drawn here, again, capacitors directly connected to one another, forming one loop, the total capacitance or the equivalent capacitance capital C is given as follows. 1 over that equivalent capacitance is equal to 1 over the capacitance of capacitor 1 plus 1 over the capacitance of capacitor 2, and so on. Again, if you plug in some numbers, you will see that adding in more capacitors to capacitors in series reduces the overall equivalent capacitance of this circuit. This is because in the loop, the capacitors must share the voltage drop, thereby not allowing them to store as much charge. In essence, you can consider the equivalent capacitance capital C as being the capacitance for a capacitor that has a plate separation D equal to the plate separation between the first and last capacitor in series. This is why the capacitance decreases as more capacitors are added into a circuit in series. For capacitors in parallel, in other words, capacitors attached in a circuit in such a way that they create more paths for the electrons to flow, then as with resistors in series, the capacitance simply directly add to each other to get the equivalent capacitance. In other words, the total equivalent capacitance capital C is simply equal to the capacitance of capacitor 1 plus the capacitance of capacitor 2 and so on. Therefore, for capacitors in parallel, as you add in more capacitors, the total capacitance of the circuit increases. Given a particular parallel plate capacitor, we can also ask, can we improve the efficiency of that capacitor? In other words, can we improve how good it is at storing charge? Thankfully, for a basic parallel plate capacitor, there is naturally going to be air between the plates. Air is considered a pretty good electrical insulator. It does not allow charge to flow through it easily. However, it is not the best type of insulator. There are better insulators than air that we can put between the plates. If we did this, this would overall increase the capacitance of that capacitor. Therefore, if we wish to increase the capacitance, we add in what are known as dielectric materials. Dielectric materials is just another term for a good insulator. For example, instead of having air between the plates, we could have a good insulator like glass or plastic. These substances are good electrical insulators. They do not allow charge to flow through them easily. Placing such material between the plates increases the capacitance by a factor kappa. Kappa is known as the dielectric constant, and it is different for different dielectric materials. Therefore, the new capacitance C prime is equal to the old capacitance capital C multiplied by this kappa. C prime is equal to kappa C. For example, it turns out that if we replace the air by, for example, glass, then the capacitance of this parallel plate capacitor will increase by a factor of about 4.7. You do not need to remember dielectric constants such as this, as they will be given to you on the test in the MCAT. Speaking of insulators, I would now like to go back to conductivity and split it up into two different categories. Remember, conductivity is a measure of how good a particular material is at conducting electricity, in other words, allowing for the flow of charge and therefore allowing for a current. Conductivity is, in a sense, the opposite of resistivity. The first type of conductivity is known as metallic conductivity. For certain materials such as metals, electrons can easily flow between the atoms within the material. Such materials are simply called good electrical conductors, as I've already stated. Metals in particular are very good at losing one of their outer electrons. These electrons are then free to move within the metal, therefore making metals very good conductors. Therefore, as I've drawn here, we have atoms within a metal which are initially neutral, but they have a tendency to lose electrons. Doing so makes the atoms positively charged and also allows the electrons to flow easily. Therefore, as I stated, metals are considered good conductors of electricity. There is, however, another type of conductivity that you need to know for the MCAT. This is known as electrolytic conductivity. Electrolysis is something I'm sure you've come across in chemistry, but it can also come up in the physics portion of the MCAT. Electrolytic conductivity is simply the measure of the ability for an electrolyte to conduct electricity. The conductivity of a solution of an electrolyte is measured by determining the resistance of the solution between two electrodes, as I've drawn here, separated by a certain distance. One final important point to note is that unlike metallic conductivity, electrolytic conductivity depends upon the strength of the solution itself. In other words, it depends on the ion concentration. For example, Deionized water naturally has a low ion concentration and therefore is a good insulator. It has a low electrolytic conductivity. Seawater, on the other hand, contains many ions and therefore has a much higher ion concentration and therefore a much larger electrolytic conductivity. Finally, I would like to finish this video by discussing how we actually measure the various quantities within a circuit. In other words, how do we measure the voltage, the current, and the resistance of different components within a circuit? To do this, we use what are known as meters. If we wish to measure current, we use what is known as an ammeter, named an ammeter, of course, because the unit of current is an ampere. If we wish to measure the current, two things has to be true. Firstly, the circuit must of course be on. If the circuit is not on, then there is no current flowing and therefore there is no current to measure. Secondly, the ammeter must be placed in series in the circuit. This is because if it was instead placed in parallel, then some of the electrons would flow through the ammeter, whereas other electrons would take the other possible path. Therefore, if we want to measure the current accurately, we must place the ammeter in series within the circuit. In a circuit, we typically represent an ammeter by a circle and a capital A within that circle. This represents an ammeter. If we instead want to measure the potential difference, in other words the voltage, we instead use what is known as a voltmeter. Again, for a voltmeter, two things must be true. If we want to measure the voltage drop across a component, then again the circuit must be on. If the circuit is not on, then there is no voltage drop across that component. As we want to measure a voltage drop, in other words a potential difference, then a voltmeter is instead connected in parallel with that component. This is because we want to calculate a potential difference, a difference in potential between two different points. That is, the potential across the component. Therefore, a voltmeter is instead placed parallel within a circuit. Finally, we can also measure the resistance of a component. Unlike measuring either the current or the voltage, measuring the resistance does not require the circuit to be on. This is because the resistance of a particular component is independent of what is going on in the rest of the circuit. Remember, the resistance of a component is equal to rho L over A. It is simply equal to three characteristics of that resistor: what the material is made of, in other words the resistivity, the length of that resistor, and its cross-sectional area. It does not care about what the current is, the voltage is, whether the circuit is on, and so forth. However, of course, if we want to actually measure a quantity, then there must be some energy involved somewhere. In other words, how are we actually reading the value? How is the value displayed to us if there is no energy, if there is no circuit? This is done by including a battery within the meter itself. An ohm meter instead typically powers itself. It does not rely on the energy that comes from the battery within the circuit in order to power itself on and measure the resistance of a component. This completes our discussion on electronic circuits and three components that typically come up on the MCAT that can be placed into a circuit, namely batteries, resistors, and capacitors. Now, as always, I would like to recap what we just learned by looking at questions of a similar style to those that come up on the MCAT. The first question is asking us about capacitors in a parallel circuit. Which of the following is the correct formula to calculate the equivalent capacitance, in other words the total capacitance, in a parallel circuit? Is the equivalent capacitance simply equal to the sum of each individual capacitance? Is it equal to the product of each individual capacitance? Is the inverse of the equivalent capacitance equal to the inverse sum of each individual capacitance? Or finally, is it equal to the product of the inverse of each individual capacitance? Well, straight away in my head, I remember that there was no products involved in any of the four formulas associated with either resistors or capacitors in series or parallel. Therefore, immediately I know the answer is not B or D. For capacitors in series, I made the point that we expect the total capacitance to drop as more capacitors are added. This is because, in essence, adding more capacitors to a series circuit makes an equivalent capacitor which has a larger plate separation D. Therefore, for capacitors in series, we expect the capacitance to decrease as more capacitors are added. This will of course not happen with option A, it will only happen with option C. Therefore, the formula for capacitors in series must be option C. Hence, the answer for this question, the formula for capacitors in parallel, therefore must be option A. Next, this question is asking us how the resistance of a particular component changes if certain characteristics of that component changes. We are asked a change in which of the following quantities does not change the resistance of a wire. Is it the cross-sectional area of the wire? Is it the current going through the wire? Is it the length of the wire? Or is it what the wire is composed of? What material is the wire made from? To answer this, let us simply recall what the formula for the resistance of a particular component is. The resistance capital R is equal to the resistivity rho multiplied by the length of that component, the length of that resistor capital L, divided by the cross-sectional area of that resistor. Straight away, we see that if we change the cross-sectional area of this wire, we're going to change the resistance of this wire. Therefore, option A does change the resistance and it cannot be correct. Similarly, changing the length of the wire capital L also changes the resistance of the wire and again cannot be correct. The resistivity rho, remember, quantifies how good a particular material is at resisting the flow of charge. Therefore, changing the wire composition, in other words changing the materials the wire is made from, is also going to change the resistance of the wire. This therefore only leaves us with option B. The resistance of the wire will not change if the current going through the wire changes. I emphasize this point by introducing the meter that is used to measure resistance, that is, an ohm meter. An ohm meter can measure the resistance of a component like a wire without the need for a current to be flowing through that wire. This is because the resistance of that wire is independent of the current flowing through that wire. Therefore, the correct answer is option B. Speaking of wire resistance, this question is in a sense also testing the concept of a wire having a resistance. The question states that the actual voltage supplied by a cell or a bunch of cells like a battery to a circuit is greater than, less than, or equal to the EMF of a cell, in other words the electromotive force of a cell, or independent of the value of that EMF. The purpose of this question is to check that you understand the fact that wires themselves have a resistance associated with them. As electrons flow from a battery around a loop through a wire, those electrons are resisted in some way by the wire itself. Every component, including the wire in a circuit, has a resistance associated with it. For example, if you roll a soccer ball from point A to point B along a typical ground, then at point B, that ball is going to have slowed down because of friction in the ground. This is something we discussed a lot in previous videos. In a similar fashion, as electrons flow from a battery around to the first component in the circuit, before getting to that first component, the electrons will have lost energy due to the resistance in the wire itself. In other words, the voltage drop across that component is equal to the energy of the cell or the battery minus the voltage drop due to the wire itself. Remembering that voltage is equal to current multiplied by resistance according to Ohm's law, then the voltage drop due to the wire is equal to the current through the wire multiplied by the internal resistance of the wire, the resistance associated with the wire itself. Therefore, the actual voltage supplied by a cell to a circuit capital V is going to be less than the voltage associated with the cell itself. Therefore, the correct answer to this question is going to be option B. The final question, as I promised, is going to look at a more complicated circuit, a circuit with resistors both in series and in parallel. The question gives us a diagram with many different resistors, some in parallel, some in series, and asks what is the equivalent resistance, in other words, what is the total resistance of the circuit. Before actually doing some calculations, let's look at this diagram and make sure we understand what is going on. First of all, let's look at the resistors on the far right. On the far right, we have two resistors that are in series, two resistors that are directly connected to one another, a 4 ohm resistor and a 2 ohm resistor. Both of these resistors are in parallel with the resistor on the left, that 10 ohm resistor in the middle branch. Likewise, the 4 ohm and the 2 ohm resistors and this 10 ohm resistor are in parallel with the 3 resistors on the left. the 8 ohm resistor and two resistors that are parallel to each other, the 30 ohm and the 20 ohm resistor. For complicated circuits such as this, we have to calculate the equivalent resistance in steps. There are many ways of calculating the equivalent resistance in this question, so if you do it slightly differently than I do here, don't worry, you are also doing it correct. To begin, I shall look at the two resistors on the right. As I said, these resistors are in series, and therefore to calculate the total resistance of just these two resistors, we simply add them together. Remember, resistors in series simply add together to get the total resistance. Therefore, the total resistance of these two resistors on the right is simply 4 plus 2 ohms. In other words, the total resistance of the resistors in the right branch is equal to 6 ohms. Therefore, I have, in a sense, replaced these two resistors with one resistor. There is now only one resistor in that right branch of magnitude 6 ohms. Let's look at the two resistors in parallel that are on the left, this 30 ohm and this 20 ohm resistor. Preferably, I would like to replace this resistor by one resistor that is in series with the 8 ohm resistor above it. As these resistors are in parallel, they have to be added slightly differently. The total resistance of just these two resistors is given as follows. 1 over that total resistance is equal to 1 over one of the resistors 30 plus 1 over the other resistance, which is 20 ohms. These two fractions can be added together to get 50 over 600. Therefore, 1 over the total resistance of these two resistors is 50 over 600. We can therefore invert both fractions and we get that the resistance is equal to 600 over 50, which is equal to 12 ohms. Therefore, the total resistance of just these two resistors on the left is equal to 12 ohms. Note also, as I stressed previously, the total resistance of these two resistors in parallel is less than either individual resistance. The total resistance is 12 ohms, which is less than both 30 and 20 ohms. I have now replaced those two resistors in parallel with one resistor of 12 ohms, which is now in series with the 8 ohm resistor above it. Therefore, we can add these two resistors easily together since those two resistors are now in series. Therefore, the total resistance of the left branch is simply equal to that 8 ohm resistor plus this 12 ohm resistor I created by adding the two parallel resistors together. In other words, the total resistance on the left is equal to 8 plus 12, which is equal to 20 ohms. So now, what do we have? In the left branch, we have an equivalent resistor of 20 ohms. In the middle branch, we still have this resistor by itself of 10 ohms. And in the right branch, we have again another equivalent resistor of 6 ohms. We now have 3 different resistors in parallel. Therefore, we can now finally get the total resistance of the whole circuit by adding these 3 resistors together in parallel, using the parallel resistor formula. Hence, 1 over the equivalent resistor of the circuit capital R is equal to 1 over the resistance on the left branch, which is 1 over 20 ohms, plus 1 over the resistance in the middle branch, which is 1 over 10 ohms, plus 1 over the resistance in the right branch, 1 over 6 ohms. Solving this, you will find that the total equivalent resistance of the circuit is 3.2 ohms. Clearly, I have mistakenly put kilo ohms in each of the options. The correct answer should be option A, which should just read 3.2 ohms. This circuit here, as I presented it, is about as difficult as it gets in the MCAT. However, it can also get confusing for students when you have both resistors and capacitors in the circuit. Thankfully, there are examples of capacitors and resistors in one circuit within the sample passages we have provided for you. Therefore, I encourage you to try these sample passages and continue practicing until you feel comfortable dealing with many different types of circuits that can come up on the MCAT. As always, let us now recap what we learned in this video. I gave a more exact definition of what current is. Current is the flow of charge per unit time. It therefore has units of coulomb per second, which we define as an ampere. I also stressed that it is important to remember that the direction of current flow is in fact in the opposite direction of which the electrons actually flow. I also defined voltage or potential difference as energy per charge. Again, it has units of energy per charge, in other words joules per coulomb, which we define as a volt. The EMF or the electromotive force was then defined as the energy associated with the battery itself. I stressed in a question that we just did that the energy that actually goes through the circuit is going to be less than the EMF of the battery. This is because the wire itself has some resistance associated with it and will therefore take away energy from the circuit. Two different rules associated with what happens with current and voltage in a circuit were then introduced. The first rule, known as Kirchhoff's junction rule or voltage law, tells us that the sum of voltages around a loop must be equal to zero. The potential difference created by the battery must be equivalent to the sum of the voltage drops across each component in a circuit. This was in a sense described as conservation of energy for a circuit. The second rule, known as Kirchhoff's junction rule or current law, instead dealt with conservation of charge. It stated that if we looked at a node in a circuit, in other words a point at which different paths ended or started, then the current into that node must equal the current out of that node. This is due to conservation of charge. Charge into the node must equal charge out of the node. As current is defined as charge per time, this also means that the current into the node equals the current out of the node. Next, I defined another property of a circuit known as resistance. Resistance is a measure of how difficult it is for electrons to flow through a particular material. The resistance of a certain material depends only upon three different factors: what the material actually is, the length of that material, and its cross-sectional area. Resistance, according to Ohm's law, is V over I and therefore has units of volt per amp. Again, instead of writing volt per amp all the time, we define a volt per amp as an ohm and has a symbol capital omega. Speaking of Ohm's law allows us to relate the three different properties of a circuit: voltage, current, and resistance. It tells us that the voltage drop across a component is equal to the current through that component multiplied by the component's resistance. I then moved on to look at both resistors and capacitors in series and parallel. Looking at potential differences through each component, I motivated what the relationship should be for resistors and capacitors in parallel and series circuits. Capacitance being the ability to store charge. I then focused in on a very simple type of capacitor known as a parallel plate capacitor. I introduced an equation which allowed us to actually calculate the capacitance for such a capacitor, and also explained how we can increase the capacitance of such a capacitor by putting a dielectric material such as plastic or glass in between the plates of the capacitor. I then briefly sidetracked and looked at two different types of conductivity that can come up on the MCAT before finishing off this video by looking at the different meters that are used to measure the different properties of a circuit. Ammeters, which are used to measure current, must be placed in series in a circuit and it can only operate when the circuit is on. Likewise, voltmeters, which measure potential difference, also require the circuit to be on but are instead placed in parallel. As resistance is independent upon what is going on in the circuit, an ohmmeter, which measures the resistance of a component, does not require the circuit to be on. Therefore, in order for an ohmmeter to actually work without the circuit on, it must be self-powered. It must itself have a battery. This video, for the most part, wraps up our long discussion on electricity. We have looked at electric fields, magnetic fields, and electronic circuits. Our next few videos, however, will still be somewhat related to this topic. For example, in 2 videos' time, we will look at light, which it turns out is a form of electromagnetic radiation. Therefore, before moving on to more complicated topics, please ensure that you feel comfortable dealing with different questions revolving around electricity. As always, I hope this video has been useful to you, and I shall see you guys in the next one.